Hi, I am Mayank Bakshi, and here I'm going to talk about our recent work in noisy group testing. This is joint work with my collaborators. Muhammad Jahan Goshai used to be a student at Sharif University of Technology. Chai Sheng is a graduate student at the Chinese University of Hong Kong, and Siddharth Jacki is also a professor here. So in this work, we look at the group testing problem. The problem is as follows. We are given a population of size n, and out of these n items, we know that d of these are defectives or diseased people, and we are allowed to perform tests of the following kind. We can group together many of these items together and perform a test. A test outcome is going to be 1 if if there is at least one defective in that group, and it's going to be 0 if there is no defective in the group. And there's also some probability that a 1 can get flipped to 0 and the 0 can get flipped to 1. So, so there are several flavors to this problem. We look at 3 different flavors. The first kind of algorithm, first kind of setting we look at is called the adaptive setting. Here, in this setting, each group that's chosen for testing can depend on the outcomes of the previous test. So that is, we can adapt to the previous test. The second kind of setting that we look at is the non-adaptive setting. Here, the groups are chosen in advance. That is, they cannot depend on the outcomes of the previous test. And we also look at something called a two-stage adaptive. Here, we can divide the testing procedure into 2 stages. The groups for the second stage can depend on the outcomes from the first stage, but within the stages, the procedures are non-adaptive. Right, so for each of these 3 cases, we come up with very fast and efficient algorithms. So we see that the number of, we list the number of tests and decoding time for our algorithms in this table, and we can see that for adaptive and the two-stage adaptive, our algorithm is order optimal, both in terms of the decoding time and the number of tests required. And for non-adaptive group testing, we pay a slight penalty in the number of tests, but as far as the decoding time is concerned, our algorithm is the fastest that's known, at least to the best of our knowledge. So here in this graph, we show these 3 algorithms in a graphical form. On the y-axis, we have the number of tests. On the x-axis, we have the number of we have the decoding time, and we can see that our adaptive algorithm lies right at the boundary of the optimal region. Here, red is the converse, which is order Dlog, which says that you need at least order Dlog in tests and decoding time. And we can see that the adaptive algorithm is right at the corner, whereas the non-adaptive and the two-stage adaptive are almost optimal. In comparison with previous work, we can see that this is much better. Alright, so let's go into the main ideas in our algorithm. The first key tool that we use is this building block called the GROTESQUE testing. What this does is, given a population of d defectives, it allows us to build a collection of tests so that the outcome is one of the following. The outcome can be that there are no defectives in the population, or there are more than one defective, that is 2 or greater number of defectives, which is d greater than equal to 2, or there is exactly one defective, and if there is exactly one defective, then it can also pinpoint which that defective is. So this building block consists of 2 parts. The first part is the multiplicity testing, which tells us how many defectives there are in the population: 0, 1, or greater than equal to 2. Alright, so this is done by just dividing this population into small pools and testing all of these pools and counting the number of 1 tests that we get. If there are no defectives, then in the noiseless setting, we should expect no no positive outcomes. If there's exactly one defective, then then the number of test outcomes that are positive, that's related to yeah. So the number of test outcomes that's positive is it should be roughly half times m1, where m1 is the size of m1 is the total number of tests, and if there are more than one defective, then we expect that there should be more number of positive test outcomes. So based on the statistical difference between these three cases, we can figure out which of these three cases we lie in. The second step is localization. So now, suppose we figure out that there is exactly one defective, then this localization test enables us to pinpoint which that defective is. And the idea here is that we use something called like an expander code, and use that expander code to somehow form the signature of each defective. So if the population size here is n, then we form an expander code of size log n and assign a code word to each individual in this population. And if there's exactly one defective, then the outcome is exactly equal to the signature, and we can then decode that signature and figure out which that defective is. All right. So based on this, we can see that if we have a way of partitioning our items in such a manner that with a high probability we end up with exactly one defective, or with a constant probability that we can figure out, we can end up with exactly one defective in a group, then we can figure out which that defective is, and we can repeat this procedure many times. So the key to this is this idea of good partitioning. So what we want to ensure is that if we partition our set of items in such a manner that there's a constant probability that every group has exactly one defective, then we can use this. We can use the GROTESQUE toolbox developed above to figure out which that defective is. All right. So now let's look at the three different algorithms, and let's see how we are going to use these two tools. So the first algorithm is the adaptive group testing algorithm. Here, what we do is we divide the testing into many stages. Specifically, we look at order log t stages. So in the first t-1 stages, we just partition the set of n items such that in each stage we recover a constant fraction of unrecovered defectives. For example, in the first stage, if we have d defectives, d unrecovered defectives, and a total of n items. So therefore, if we partition this into sets of size n over t, then with a high probability there would be a constant number of sets which have exactly one defective. And based on the GROTESQUE testing on each of these sets, we can figure out which the defective is. Now in the second stage, we can exclude the defectives that have already been decoded, and then partition the remaining defectives in accordance with the number of into many sets, and the number of sets depends on the number of unrecovered defectives in the second stage. And finally, we can repeat this procedure log t times, so that finally we can recover all the defectives. The last stage here is slightly different. In the last stage, we just look at a coupon collection procedure where we keep on testing random subsets until we figure out all the defectives. And we show that by having order log t stages in all, we can figure out all the defectives. So finally, and also we can finally compute the total number of tests required, and we can show that this is equal to order d log n. I won't go into the analysis of the complexity, but it's also easy to show that the complexity of decoding is order d log n. All right. So now let's look at non-adaptive group testing. Here, unlike the adaptive group testing, where we could exclude the decoded defectives in the second stage, we can no longer decode. We no longer know what defectives are going to be decoded in the first stage, and exclude them in the second stage. So as a result, we have to partition all the n items in all stages and test all of them in all stages. And because of this, we have to pay a penalty of log d in terms of the number of tests required. And we can show that order d log d times log n number of tests suffice. All right. Finally, we also look at two-stage adaptive group testing. Here, we use the idea of birthday paradox. So first, let's partition this set of n items into order d cube sets. Then, with a high probability, each of these sets will contain at most one defective by an argument similar to the birthday paradox. All right. So now let's focus on the sets here, and we'll call a set to be a defective if it contains one or more defective items. And out of these order d cube sets, we know that d of these are defectives. So now we can perform a non-adaptive group testing on these d cube items, d cube sets, to figure out which the defective sets are first. So this is the first stage of the algorithm, which is to figure out which of these sets correspond to defective items. And the second stage is to perform localization tests on only those sets which correspond to the defective items. So this way, by using two stages, we can perform group testing in an almost optimal manner. All right. So here we have considered three different kinds of algorithms. Obviously, there is scope for improvement. For example, in the non-adaptive group testing, we pay a penalty of log d. So obviously, there's a future direction possible, which is motivated by the question whether there exists a non-adaptive group testing which has both order optimal number of tests as well as the decoding complexity. And you can look at our paper, which is available as a preprint at this website. And thank you for listening.